All right, hello and welcome. Today, we're going to dive into the invisible force that, well, powers pretty much everything in our lives, electricity. But here's the thing, it's not just one thing. It actually comes in two very different flavors, and the story behind them explains a really common mystery you've probably seen every day and never thought to question. Seriously, think about it. Why does your super sophisticated smartphone need this clunky block to get its juice, while a power-hungry beast like your toaster or washing machine just plugs right into the wall with a simple cord? It seems completely backward, doesn't it? Well, that little brick is basically a translator. It's taking one kind of electrical language from your wall and converting it into a totally different language that your phone's battery can actually understand. And that simple act, right there, it opens up this huge divide in how we make, move, and use electricity. So, to really wrap our heads around this, we need to start with the basics. What even is electricity when it's moving? Let's get down to the absolute foundation, the electric current itself. Okay, so picture a wire like it's a pipe. An electric current is nothing more than the flow of zillions of tiny particles called electrons moving through that pipe. It's the energy from all these moving electrons that we're harnessing to do everything, from lighting up a room to powering a supercomputer. The huge difference, the one that changes everything, is how those electrons move. And this brings us to our two main characters in this story. First, you've got direct current, or DC, where the electrons just flow in a nice, simple, straight line. And then you have alternating current, or AC, where the electrons are constantly changing direction, zipping back and forth in a sort of wave. Let's get to know our first character, direct current. Now, DC is the simpler of the two, for sure, but don't let that fool you. It is absolutely critical for the technology that basically defines our modern world. The best way to think about DC is like water flowing through a garden hose. It's smooth, it's steady, and it only moves in one direction, from the spigot to the nozzle. The flow of electrons is constant, unwavering. It's a one-way street for energy. So, these two properties really define what DC is good for. The one-way flow is straightforward, but it's that constant voltage that's the real key. It provides the stable, totally predictable supply of power, and that is absolutely essential for the sensitive microchips inside our electronics. Any little fluctuation could cause a total system crash or even damage the hardware. And this is exactly why DC is the language of anything that stores power. It's what you'll find in every battery, it's what solar panels generate directly from the sun, and it's what powers all of your portable gear, your laptop, your phone, even your electric car. So that bulky brick on your charger, all it's doing is taking the wall's AC power and converting it into the nice steady DC your device's battery needs to charge up. All right, let's switch gears and talk about our second character, the one that powers pretty much our entire world, alternating current. AC is a little more complex, for sure, but its strange properties are the whole reason our global power grid can even exist. So, unlike that steady march of DC, the electrons in an AC system are, well, they're constantly changing their minds. They rush forward for a tiny fraction of a second, then slam on the brakes, reverse, and flow backward. They don't actually travel very far down the wire, they just kind of wiggle back and forth in place, passing energy along as they do. So the two things that defined AC are this reversing flow and a voltage that changes right along with it, flipping from positive to negative and back again. Here in the US, this happens 60 times every single second. And as we're about to see, this constant change is the secret ingredient to AC's superpower, its ability to travel huge distances without losing all its energy. So where do we find AC? Everywhere. It is the undisputed standard for distributing power on a massive scale. It's what flows from power plants, through those giant transmission lines, and into every outlet in your home. It's also perfect for big appliances with motors, think refrigerators or washing machines, because that back and forth current is incredibly good at creating the spinning force they need to work. And now we get to the real heart of the story. Why have two different systems? I mean, why not just pick one and stick with it? Well, it all boils down to solving a massive engineering problem. How in the world do you send electricity hundreds of miles away without it all just fizzling out? This is the million-dollar question, right? We live in a world packed with DC devices, but we plug them all into an AC grid. It seems so complicated. Well, the answer isn't about convenience. It's about the cold, hard physics of moving power. You see, anytime you push electricity through a wire, that wire fights back a little bit. It has resistance. Think of it like friction, and that friction turns some of your precious electrical energy into useless, wasted heat. If you tried to send low-voltage DC power a few hundred miles, almost all of it would just get lost as heat before it ever got to your house. And this is where AC has an absolutely brilliant solution. At the power plant, the AC is generated, and then it's sent through a device that steps up the voltage to incredibly high levels. We're talking hundreds of thousands of volts. By jacking up the voltage, you can send the same amount of power with way less current. And less current means way less energy lost as heat. Then, once the power gets near your city, another device steps down the voltage to a much safer level for you to use at home. And the hero of this entire story is a device called the transformer. It's an amazing piece of engineering that uses magnetism to change voltage up or down. But here's the catch. It only works if the electric current is constantly changing, because that's what creates a changing magnetic field. The steady one-way flow of DC, it creates a constant magnetic field, which just sits there and does nothing for the transformer. This single advantage, the ability to easily change voltage, is why AC won the battle and became the king of the power grid. So there you have it. We've got these two very different types of electricity, each with its own unique strengths, that have together built the world we live in. Let's pull all this together now and see where the story's heading next. So let's just recap. On one hand, you have DC. Its flow is stable, its voltage is constant, which makes it perfect for delicate electronics and for storing energy in batteries. But it's terrible at traveling long distances. On the other hand, you have AC. Its flow is wild, and its voltage is always changing, which isn't great for a microchip. But that very same property lets it work with transformers, making it the undisputed champion of getting power from the plant to your plug efficiently. But you know, the story doesn't end there. In a really fascinating twist, DC, the original runner-up, is making a massive comeback. And why? Because our entire clean energy future is being built on it. Solar panels, for example, naturally generate DC power. And batteries, they can only store power as DC. So now we're building a world with all these local sources of DC power that have to somehow play nice with our old-school AC grid. And this brings us to one last really interesting question. The first Great War of the Currents was won by AC, all because it was better at long-distance travel. But what about a future where we generate a lot more of our power locally, from solar panels on our roofs, and store it in batteries in our garages? Is AC's reign still secure? The truth is, the future probably won't be about one winning over the other. It's going to be about building a much smarter, more complex system, a true partnership between these two powerful forces. And that is a story that's still being written right now.